For any exam-related queries, call us at +1 678 648 4277. You can mail us at info@livexamhelper.com or reach us at https://www.livexamhelper.com. 1. You want to make a magnetic actuator, that is, a magnetic material that will strain and do work when a magnetic field is applied. You decide to use a rectangular prism of polycrystalline Ni. Ls is almost equal to -34x 10 to 6. The prism measures 2 by 10 by 100 mm. Assume a modulus E equals 1011 n/m2. A. What direction will you apply the field along to get the greatest extension? B. What is the shape anisotropy and demagnetizing field for magnetization in that direction? C. How does that compare with the anisotropy for single crystal Ni? K1 is almost equal to -6x 103j/m3. D. What field would you design for? How many turns? How much current to achieve this? E. Write the expression for the free energy including external field, anisotropy, magnetostriction, and an external stress of 100 MPa opposing the Ni extension. Compare the magnitude of the terms. livexamhelper.com. F. Calculate and plot the field dependence of magnetization. G. Calculate and plot the field dependence of the strain. 2. You have a process for making nanoscale magnetic particles with typical aspect ratios of 5:1. You want to make some very small but thermally stable particles. A. Describe quantitatively your considerations in choosing between Fe 0.6 Co 0.4 and Co, assuming you could make either of these compositions with 001 crystal direction along the long particle axis. Consider the following: I. Crystal structure. 2. Magnetocrystalline anisotropy. 3. Shape. Magnetostatic anisotropy. 4. Single domain particle size. And V. Superparamagnetic limit at lab timescales, 1 second. B. If the particles were superparamagnetic, compare the susceptibility of particles of the two compositions having the same shape and volume. livexamhelper.com. A. What direction will you apply the field along to get the greatest extension? Largest extension will be in longest direction. The easiest direction to magnetize in to achieve this is the next longest direction, y equals 10 mm. The free elongation in y is Lx 100 mm equals -3.4 microns, while x and z dimensions extend out by 1.7 microns each. B. What is the demagnetizing field and shape anisotropy for magnetization in that direction? livexamhelper.com. X. 2.22 and 2.23 indicate New York is almost equal to 2t/px10 equals 0.13 and n is almost equal to 2t/px100 equals 0.013. The demagnetizing field is Dmag is almost equal to New York ms equals 61 Ca/m, less than 760 OE. The shape anisotropy is, therefore shape is almost equal to m0 ms, h hertz, Demag/2 equals m0, n nz. m2 divided by 2 is equal to 17 kj/m3y yseyz, using m0 ms equals 0.6 t for Ni. C. How does that compare with the anisotropy for single crystal Ni? The shape anisotropy, 1.7 by 104j/m3, is greater than the crystal anisotropy, which in turn is greater than the anisotropy of the polycrystal Ni. So shape dominates the magnetization process. D. What field would you design for? How many turns? How much current to achieve this? I would design for at least 1 Co 80 Ca/m applied along Y. 2 air coils of rectangular shape as pictured right could suffice if heating is not a problem. Otherwise, you will need a soft iron core, fewer turns at the cost of more weight. A first guess at the ampere turns needed to generate the field would be from the field at the center of a circular loop having the same circumference as the loops at right. LiveExamHelper.com. This gives H is almost equal to Ni/0.2. Thus, to get 80 Ca/m would require 16 amps through about 1000 turns. A more careful calculation would involve piecewise consideration of field from the different legs of the rectangular loop. Write the expression for the free energy including external field, anisotropy, magnetostriction M, and an external stress of 100 MPa opposing the QNI extension. Compare the magnitude of the terms. Assume the magnetization has no component along X. The Me term is LiveExamHelper.com. Check that each of these terms makes the energy change in proper direction as field and stress change. The shape anisotropy was calculated to be 17 kJ/m3. The magnetostrictive anisotropy is about 34x 10 to 6, 2x 1011 almost equals 0.12 kJ/m3, and the external stress anisotropy is of order 1.5 times 34 times 10 - 6 times 108 almost equals 5 kJ/m3. The shape and external stress anisotropies govern M, H. F. Calculate and plot the field dependence of magnetization. We know the solution to is cos equals M equals H, but now K, the term in, is influenced by the shape and external stress. With increased stress makes it harder to saturate. G. Calculate and plot the field dependence of the strain. LiveExamHelper.com. To calculate the actual strain, you need to add an elastic energy term, 1/2 E2, to F. The total energy density can be simplified using cos equals when taking derivative of F with respect to strain. Keep in mind that H equals H/H is also a function of strain. So LiveExamHelper.com. 2. You have a process for making nanoscale magnetic particles with typical aspect ratios of 5 to 1. You want to make some very small but thermally stable particles. A. Describe quantitatively your considerations in choosing between Fe 0.7 Co and Co 0.3, assuming you could make either of these compositions with 001 crystal direction along the long particle axis. LiveExamHelper.com. Crystal structure. Fe-Co alloys have BCC structure up to about 90% company. Co is hexagonal except when impure or processed by non-equilibrium methods, in which case it is usually FCC. 2. Magnetocrystalline anisotropy. 70% Fe-Co has K1 equals plus 3.5x 104J/m3 easy, whereas Co has K equals plus 4.1x 105J/m3 with an easy C-axis. Based on magnetocrystalline anisotropy, UHCP-Co would be more thermally stable, as also would be FCC-Co. K1 equals minus 1.2x 105J/m3. 3. Shape. Magnetostatic anisotropy. 70% Fe-Co has M0M is almost equal to 2.4 T. M0M2 is equal to 4.6x 106 kJ/m3 SS, whereas Co has M0MS equals 1.7 T. M0M2 is equal to 2.3x 106 kJ/m3. Based on magnetostatic energy in AS low symmetry particle, Fe-Co would be more thermally stable.